Hi guys, today our video is going to discuss the concept of the electric field. Let me just go back one slide real quick. So if you think last year when we talked about fields around objects, the only thing we really discussed was the idea of the gravitational field, and this is supposed to be a planet. So we kind of imagine that the gravitational field extends away from an object that has mass, and anything that comes into this gravitational field will therefore experience an attractive force towards the planet. So charges have kind of the same scenario happening. We have positive charges and negative charges, and both of them exert a field around themselves. We call this the electric field. And this field is what's responsible for causing electric forces on other charged objects. So let me talk a little bit about how we draw it and what it looks like, and then we'll talk about how to calculate it. So the charges, and the field lines that we draw around the two different charges, positive and negative, look a little bit different. So around a positive charge, the field lines begin on the positive charge and radiate outward. So you can see here in this graphic, we have a positive charge, and all of those arrows come out from it like this. Negative charges are the opposite. We can see in this graphic that the field lines end on negative charges. And the reason why we do it this way, I'll explain in one quick second. So a couple of things about drawing field lines. Besides this general geometry here, the lines begin on positive, end on negative. The spacing shows us proportionally the strength of the field. It also, the number of lines that we draw also will show us the amount that the charge has, the strength of the charge. So what this means is that the more lines you draw, the larger or stronger that charge should be. So in this bottom graphic down here, we have a positive charge and we have a negative charge. This positive charge has a lot more field lines radiating from it than the negative charge. So this one will be much stronger. Also, the second bit, the spacing of the lines shows us the strength of the field. So what this means is that these field lines will radiate outward and get farther and farther away from each other as they get farther and farther away from the charge. The strength of the field is inversely proportional to the distance. So the bigger the distance, the smaller the strength of the field. This is very much like your gravitational field idea, that the farther away you get from the planet, the less effect you feel from that planet's gravitational field. And so the reason why we draw our field lines like this, I guess I should add a little addendum here and say that it's important that you guys understand that field lines don't really look like these super straight lines. This is just a convention that we use to draw them so that we can kind of understand what's happening visually. The field is really kind of more like a cloud, I guess, or a region that just extends out past the charge. But the reason why we draw these arrows pointing away from a positive and towards a negative is, and this is kind of like an important thing, I guess you guys should have probably added as an addendum on here. Field lines are drawn to represent the path of a test charge. So what does that mean? A test charge is, whenever we talk about test charges, we're talking about a tiny little charge that we're going to put in a field somewhere and observe its behavior. And test charges are always positive. So essentially what this is saying is that the field lines are drawn to represent the path of a positive test charge. So if I put a test charge right here, keeping in mind that they are always positive, what direction is that going to want to go? Well, this is a positive charge, and this is a positive, so it's going to want to flee or go away. If I put a test charge here, positive, negative attract, it's going to want to come close to the negative. So this is just a convention that we set, or that was set for us a long time ago when people didn't know very much about electricity, and they decided that positive charges were responsible for electricity, and positive charges were the ones that moved everywhere, and so we kind of just set this idea and this convention in place. Okay, so let's talk about math, because the next slide is a practice problem for us to do. So there are two different ways really to talk about the field, and it depends on what you are trying to find. So the electric field, and this is going to be due to a charge. So I have a charge out here in space. It's a positive charge. Let's say it's generating a field. What is its electric field at a particular distance away from it? So this is our formula for electric field. KQ over R squared. Q being the charge, and R being the distance. Again, we have this inverse square relationship. So the electric field is inversely proportional to the square of the distance away from the charge. This looks very similar to Coulomb's law, right? KQQ over R squared. So this is our electric field. Another way to relate electric field and electric force is to say that the force a charge experiences depends on the charge and the field that it's sitting in. So if I wanted to rearrange this, I could say electric field is equal to F over Q. And this would describe for me, if I have an external field, right, this field being generated by this charge, I could use this expression to figure out the force that a second charge would have if I put it in this field. So here's our, we'll label this one Q1, and we'll label this one Q2. So if I put this second charge inside of this field, what force will it experience? What force will this Q2 feel in this? And we'll say this is Q1. And we'll call this E1 because this is the electric field due to Q1. So this is a really important relationship here, here, and here. These two guys work together a lot to figure out forces or maybe charges, whatnot. So let's take a look at an example that we can do to see how this all comes together. So positive point charge Q1 plus 4 nanocoulombs is on the x-axis at x equals -1. And a second charge is at x equals 3. So let's kind of draw this line out here. Put a 0 over here. Here's -1. This charge is plus 4 nanocoulombs. And then we have 1 at x equals 3. Not to scale, obviously. And this one is plus 2. So find the net electric field at a point A on the x-axis at x equals 6. And at a point on the x-axis at x equals 2. So electric fields are vectors, which means that we add and subtract them as such. So the direction becomes super important. So for port A, let's take a look. At a point on the x-axis at x equals 6. So what is the field going to look like at x equals 6? I'm going to just kind of extend this out just a little bit, and we're going to say 6 right here. So we have two charges that are going to contribute to the electric field at this point. And these two charges both have their own electric field at this moment. So let's take this first one, positive 4. The electric field at this point, because of this positive 4, is going to be pointing to the right. Because remember, electric field goes away from the positive charge. The electric field due to this guy is also going to be pointing to the right because he's positive as well. So we're going to have two electric fields at that point that will add up to be the total electric field at that point. We're going to add them because they are going in the same direction. If one was pointing this way, we would, of course, subtract them. So let's do the electric field due to this guy. So that's going to be KQ over R squared. And this one will be KQ2 K, and then Q1 is 4 times 10 to the negative ninth. All that. This is 6 plus 1, that's 7 squared is the distance. K cubed 2, K, 10 times 10 to the negative ninth. All over, and that's a difference of 3, so 3 squared. So this first term, when I multiply that by K, becomes 36 divided by 49. And then this one becomes 9 over 9. So we just have to do 36 divided by 49. All right. So when I do those together, my electric field total is 1.73. And if you want to be super specific, electric field is measured in newtons per coulomb. And we can say it's in the positive I, or we can say along the positive X, or whatever. All right, next one. At a point on the x-axis at x equals 2. So now we're going to be somewhere in the middle between these two charges. So what's going to happen? Well, they're going to, here, so this is 2. Now this guy's field is pointing this way, and this guy's field is pointing this way. So we're going to end up subtracting these two values. So same setup. So this is K, Q1, 4 times 10 to the negative ninth. R squared, now this is 2 plus 1 is 3 squared. And this, K, 10 times 10 to the negative ninth. Now the difference between 2 and 3 is just 1. So, this is 36 over 9 plus 9 over 1. 90. Ooh, I think I messed that up in the last one. I think that should be on the last example. It should be 90 over 9. Ah! I'll have to go back. You guys have to go back and fix that. All right, so this is 36 and this is 90 over 1. So 36 divided by 9, that is 4. And then 90 divided by 1 is 90. So that makes your electric field at this point be 94 nanonewtons per coulomb. And so I'm sorry, I'm pretty sure 90 divided by 9 is 10. So this should be 10.73. Okay, so I want you guys to try to do part C on your own, just so that I don't make this video too long with my examples. What is the force on a 2 nanocoulomb charge at each point? So we know the electric field at each point, right? And we're going to stick a second or a different test charge in that field. So we could use this expression, right, to figure out what our force will be. Okay, so acceleration of charges in any field. So it's kind of important to understand that sometimes you guys will get questions that marry the idea of electric force with our previous understanding of kinematics. And forces are forces, right? F equals ma applies to every single force that we can possibly have. So if you're in a situation where the electric force is the only force on a particle, then that electric force will become your net force, right? And that electric force will equal ma. So sometimes it'll ask you to find the acceleration of a particle through a particular field. And this is the relationship as to how you would do that. So if you guys remember from chemistry, this guy, J.J. Thomson, discovered electrons by shooting atoms through a charged electric, or through an electric field and measuring how far they moved and what they did. All right, so here is an example. Electron is projected into a uniform E field of 500 nanonewtons per coulomb. I don't know why I keep trying to say nanocoulombs. That's not correct. Okay. The initial velocity is 1.86 times 10 to the 6th meters per second. How far does the electron travel before it's brought to a rest? Okay, so in this case, the only force it's experiencing is the force that comes from being in this electric field. So F equals QE. And this is going to be a force that slows it down, right? The electric field is pointing this way. So remember, it's pointing along the eye. So remember that this electric field points in the direction that a positive charge wants to go, but this is a negative charge. So that force will, in essence, be slowing it down. It wants to go the other direction. So using this and the charge on an electron, 1.6 times 10 to the negative 19th, we can figure out our net force. And then we can use that net force and F equals ma to figure out our acceleration. The mass of an electron is 9.11 times 10 to the negative 31st. Once we know our acceleration and we know our initial velocity, it's coming to a stop, so we know our final. We can use a kinematic to figure out how far the electron travels before it comes to a stop. I'm going to let you guys go ahead and do the plug and chug now that I kind of showed you how to set that up, and we'll check that the next day. So this is a cathode ray tube, and this is what is in the TV that's in the corner of my room that I want to break it apart and take a look at. But what happens is you have an electron gun in your TV, and so it generates an electric field between these little plates. And as the electron shoots through there, it gets deflected by the field that's happening between these plates. And it gets deflected in different directions. And those electrons striking the screen in that particular pattern is how you guys see the image that you do on the television. So I really want to break that apart and go through it with you together one day so that we can take a look at it a little bit closer. Okay, so this is the last little conceptual thing we need to, I guess, discuss, and that is dipoles. Dipoles are a positive and a negative charge that are really close together, and so they kind of form one little unit. You can kind of see here in the drawing this positive charge and negative charge. I'm sorry, it kind of showed up a little weird. But the field between them exists like this, right? So if I put a dipole in an electric field, let's say I have an electric field going this way. Well, the positive charges are going to experience a push this way. The negative charges will experience a force to the left. And the whole thing, both of those things added together, will create a torque on the dipole, and the dipole will spin inside of an electric field. We're not going to talk too much about what that torque, how to calculate it, or anything else really. Just understand that it happens. That if I put this dipole in an electric field, this phenomenon, this spinning thing would occur. All right, one little last thing, and then we're going to be done with talking about electric field for now. Electric fields and conductors. You guys can read through this beginning part, but if you have a sphere that is metal and it's hollow or solid, it doesn't really matter. If you were to add charges on this sphere, well, charges move really easily across the surface of a conductor, and all of those charges don't want to be close to one another if I put a whole bunch of positives on top of this thing. So what happens is that these charges spread out so that they only exist on the surface of the conductor. There is no electric field and no charges on the inside. And that's because they all hate each other and they want to be as far away as possible from one another. And so they're all going to spread out on the surface until they're roughly in equilibrium and they don't move. So two very important key concepts. Number one, the electric field inside a conductor anywhere below its surface is zero. This is always a test question in some capacity on the E&M test. The second thing is that the electric field outside the body of the conductor must always be perpendicular to the surface. And then I have a little graphic on the next page. So here is our surface of our conductor. All of those charges reside on the surface of it. And the electric field shoots out kind of like sunshine rays from the surface. But they are all perpendicular to the surface of the conductor. And the electric field inside is zero. We're going to talk more about this phenomenon right here when we get to talking about potential, but it's important to understand that when you have a misshapen conductor, something that's not a perfect sphere, regions that have smaller area will, or a smaller radius of curvature, that is where the charges like to concentrate. And that has something to do a little bit with electric potential, but when we talk about that, we'll revisit this idea. But that is all I want to discuss with you guys today.